All right, this is the second lecture of the same series, Kinetic and Molecular Theory of Gases and Graham's Law. I'll be spending time on Graham's Law here and then going to our homework ditto that I gave you. But before we go forward in Graham's Law, we have to show that what kinetic and molecular theory was all about. As I say here in this slide, this ideal gas law equation describes how gas laws behave. So we've talked about how pressure, volume, moles, okay, affect each other in terms of the different variables that affect a gas. And it basically, again, explains how gases behave. The kinetic molecular theory is a model that aids in our understanding of what happens to gas particles as environmental conditions change. This is basically the why. And it's centered around, again, kinetic, motion, okay, and the molecules. Because these motions, as we said, are independent, okay, if they are ideal, okay, then we can see clearly that, hopefully anyway, that the pressure, volume, temperature, mole relationships we built in the ideal gas law should work perfectly. But as we talked about, there is attractive forces. These guys do take up some size. Real gas really have volume, and real gases really have attractions, so there is some deviation. But where we're moving from now is how all these particles will actually mix into the room. Okay, so the main tenets of the kinetic molecular theory are, in fact, about basic motion and how their motion in terms of their independentness, how well they are independent. Now, as we've talked about already, the average kinetic energy of a molecule, and this is again explaining why they behave, is proportional to absolute temperature. We've drawn and talked about these Boltzmann distribution graphs in other lectures. You can see that a gas under higher temperature, this area under the curve is stretched out. This represents the molecules that have speeds, which is tied to motion, average kinetic energy, which is below the mean, and here are some speeds above. When you have a temperature, it's an average range of motion, okay? When you're colder, you're pushed up against that zero, so you kind of stack up higher. So as you get warmer, this graph actually spreads out, okay? And again, we talked about that. And here's another example of it. What we haven't talked about, though, is that when temperature stays constant, okay, for two different gases, believe it or not, their translational motion is different. So let me just play this video for you, and then I'll come back in and pick this up. We're about talking about gases, and even though you may be at the same temperature, what is new to us is that this motion translationally, left to right, remember, motion in molecules is rotational, translational, and vibrational. Okay, so the average kinetic energy is taking into account all of those motions, but the translational motion is different for big molecules and small, and I'll show you mathematically why that works. Let's just play this video.
At any given temperature, the molecules of a gas are in continual motion. At any instant, some molecules have more kinetic energy of motion than others. With increasing temperature, the average kinetic energy increases in proportion to the absolute temperature. This graph shows the distribution of molecular speeds for a particular gas at two different temperatures. Notice that the most probable molecular speed, given by the peak of the curve, increases as the temperature increases. Here we see a mixture of two gases with different molecular masses, helium and neon. The more massive neon atoms move more slowly, but they possess the same average kinetic energy as the helium atoms. At a given temperature, the
Now, how is that? How can helium and neon move at different temperatures? Let's take a look at that for a second. So let's get back to this. How can this be? We know that helium has an atomic mass of 4. We know that neon has an atomic mass of 20. And where I'm getting this, okay, is from the periodic table. Just take a quick little review there. So the periodic table, okay, it's not working. Okay, so back to the periodic table. You know, again, I know most of you guys know this, but there's always somebody who doesn't. Remember that top number is the relative mass, okay, and I'm looking at my neon, and there's a 20 right there. All right, so that's where I'm getting that atomic mass from. And the helium above it is 4, and they're based on each other. Okay, so back to where I was doing. So we have two different gases in that And we have our helium, which is monoatomic, and then we have our neon. And they're both the same temperature, same average temperature. Yet, as the animation was showing, the helium was translating or moving from point A to point B much faster than the heavier molecule. How can that be? They have the same temperature. That bothers a lot of people, and it certainly bothered me when I first learned it. But when I think about motion, think about there's a vibrational motion, okay, then there's a translational motion, which we're talking about when you mix into a room. Then you have the rotational motion, okay? The bigger you are, even though you may have the same kinetic energy, the bigger objects are going to have more rotational and more vibrational energy. They just can't move the same way. And now, if you don't visualize that, think of the Earth, okay? I know that we're moving around the sun, but we're also spinning at a very fast rate, okay? And the reason why we're spinning is we're such a large object, okay? We have a lot of rotational motion. Now, again, the motion of atoms and planets are not exactly the same. There's different theories and laws between them, quantum mechanics being one. In any case, it's something to think about. Now, there's also this mathematical relationship. Kinetic energy, by definition, motion energy, and it's a combination of vibrational, okay, rotational, and translational. I don't think I wrote those next to my pictures, but we get to the point. The rotational, okay, is here, vibrational is here, and translational is moving from a distance from A to B. Rotational is the object rotating, and the vibrational energy is that vibrating, so to speak. Any case, kinetic energy, which is the combination of all three, is equal to 1/2 m mu squared. Now, this is mass, this is velocity. So we're considering the velocity, and that's really translationally, okay? So 1/2 the mass velocity squared. So if you think with me, okay, and let's get rid of some of these things here. If you think with me, we have two gases. Let's do helium. Let's do neon. Okay, now, let's pretend they're both at the same speed. Let's make this 100. So they both have 100 units of kinetic energy, 100 joules, because kinetic energy is a unit of energy, so these would be joules. Okay, and it's both under 1/2 m mu squared, or u squared, v squared. Many people use different words there for that velocity. We'll just keep it, let's make it just v squared. Okay, so what times each other? Helium has a molecular mass, okay, let's do 4 grams per mole. Neon is 10 grams per mole. So if we had a mole of that, that's be the value. So 1/2 4, okay, is 2. 2 times what equals 100? 2 times 50. 50. Okay, so the velocity for helium would have to be 50. And the velocity for neon, 1/2 10, is 5. 5 times what is 100? 20. So we can clearly see, hopefully, that by the masses being different, it makes our velocities different. And it could clearly see that the heavier, okay, heavier neon is going to have a lower velocity. Whereas the lighter, okay, the lighter mass of the helium is going to have a higher velocity. So at the same temperature, okay, helium is going to velocity translate more, okay, than the slower moving neon, because it is lighter. It is more ideal. It is faster, more independent than the slower moving neon. It has less attractive forces. It kind of explains. So if you were to draw a graph of these two, okay, gases. Okay, Boltzmann distribution. This is going to be speed, or I should say velocity. Okay, and this is going to be number of, let's say, atoms, since these are atom monatomic molecules. This would be the distribution of speed, let's say, for neon, and this would be remember, the same temperature, because they have the same average kinetic energy. So the same temperature, this would be the same distribution, or the distribution for helium. Look at that. Helium has a lot more molecules that are moving at a faster rate than neon. There's still a range, because speed and kinetic energy, there's an average motion. But helium has a lot more molecules that are moving faster on average than neon. So if we had a gas leaking helium out of a container, and we had a neon in a container, the one that would escape into the gas, into the opening area, or diffuse faster would be helium, because it's the most ideal, it's the lightest, more independent, therefore it can diffuse faster. The heavier gas, which is more real, okay, won't mix into the room as fast, okay, and that's essentially Graham's law of diffusion. However, there's something called effusion. If you had, let's say, a balloon of helium, and you had a balloon, okay, terribly drawn, but you get the point, of neon, which one is going to empty the balloon faster? Well, in latex, there is little porous openings, and helium gets out. We all know that buying helium balloons, by the end of the day, if they're regular latex balloons, they go to the ground, because the helium, being lighter, more ideal, and faster, can escape the little opening much better than the neon. So I blew up 2 balloons the same size, and I waited a couple of days. Okay, the helium will be more deflated because it can effuse, escape the opening much better, because it's going faster on average than the neon. Neon still escapes, but not as fast. Therefore, it will stay inflated more. You guys know this. When you blow up a balloon with regular air from your mouth, it stays inflated. When you blow up a balloon with helium, it deflates fast. These guys are moving faster at the same temperature because they're lighter and more ideal. That essentially is the basis for Graham's law of diffusion. But we have a mathematical relationship. Let's do that. Let's take helium, or 1/2 mv squared. Let's do neon, 1/2 mv squared. They're equal to each other because they're the same temperature. Maybe, let's pretend it was, I don't know, 273 Kelvin. Doesn't really matter, they're equal. Now we have, let's solve for the velocities of each. So I'm going to divide this side by the 1/2 m. So what I did was I solved for v squared, and I'm going to bring this v over. So what I'm doing is I'm taking this component of kinetic energy, right, and I'm solving for this blue v squared, and I'm going to put this in the bottom. All right, now what I'm going to do is I'm going to solve, I basically want to take this equation and I want to see how one velocity compares to another. So I'm going to take this v squared over here, which is due to the neon. Okay, let's go back to black. And I'm going to move it down here algebraically. So this went to the bottom algebraically, this went to the bottom here. So when I multiplied this side, for those people that are still lost, I'm sorry, okay, 1/2 m on this side, 1 over, so that would cancel. And I multiplied this side by 1 over 1/2 m. Okay, it's a different 1/2 m, so that's why that went to the bottom. Okay, let's rewrite this. V, let's make sure I have, let's make this same color. Okay, and what I have is, make sure this is blue, v squared, which is the helium's rate, okay, over, let's go black again, v squared of the neon. So we look at the velocity of helium compared to the velocity of helium. Now what does that equal to? Well, where did this 1/2 m come from? It came from the neon side. I'm sorry, helium side. This is helium, and this is neon. Okay, so this went on the bottom. I think I'm in blue. I wasn't. And this gives me 1/2 m. All right, this was already here because this is the neon side, so let's go back to black. 1/2 m. Okay, notice something. It's an inverse relationship. The velocity of helium is directly related to the inverse of its mass, molecular mass, we say, mass per 1 mole from the periodic table. And same thing here. The velocity of neon is inversely related to its 1/2 mass. Now I can do some canceling here, can't we? People are probably saying that already. I'm going to cancel out the halves. I can't cancel out these masses because they're different atoms. Okay, I'm going to get rid of the square, so I'm going to square root both sides. Well, what does this give me? Let's go black to back. This is going to give me, okay, the square is going to go away, so I have the velocity of neon square root, oh no, 1/2, the m, this is of neon, and I have sort of blue. I have the velocity of helium. This is the molecular mass of helium. And this is Graham's law. Okay? Let's get rid of that. Oops, not all of that, but hey, rock on. So what we have is how fast helium moves out of a hole, effuses, or mixes in a room, diffuses, compared to neon. That rate of mixing is inversely related to the square root of its molecular mass. Okay, so let me just rewrite this. So the rate of helium, how fast it diffuses, and I'm just changing the velocity to how fast to rate, to the rate of how well neon, okay, is equal to the square root of the molecular mass of helium, molecular mass of neon. Notice they are on opposite sides. It's an inverse relationship, just like we had what? Volume was inversely related to 1 over p. It's an inverse relationship. So this is what you're going to use to do these problems. Let's go to your homework ditto. Okay, so in this ditto, this worksheet here, the first side's pretty simple. I want you to look up the densities from table S in your reference table. Okay, you should notice that this Cl2 is going to be the most dense. Put that density in. Okay, and then you can look at the relative atomic masses, or the masses that we just talked about for helium or neon. It's the relative atomic masses. You're going to put them in. Don't care about them being what? Diatomic. It's for the individual masses. The Graham formula, or molecular mass, is the mass per 1 mole of this particle. So if you look up chlorine, chlorine is 35.4, so if you take it times 2, it's about 70 grams per mole. Chlorine is 35 AMUs, atomic mass units, when we talk about the atoms. So you're going to put densities here of table S, just put them as written, and you'll notice something. The things that are the most dense, okay, will have the heaviest atomic masses and have the biggest molecular masses. So please go through that. Now, rank each order of increasing speed. How well? Well, this you're going to see from the above data is the heaviest, most dense, biggest atom and highest molecular mass. It is going to be the slowest, so that would be 4. Whoever is the lightest will be number 1 and in between. Okay? Which would have the slowest rate of diffusion? Now I'm giving you an atom and 3 different gases. The best way to do this, if you had densities, great. If these were all atoms, you could use from the periodic table each atoms. But what we can do is do a molecular mass, which is that big M there. Find the grams per mole of each of these. Who has the heaviest amount of atoms per seat? Who has the highest molecular mass? That one is going to go the slowest because it's acting the most what? Most real. Number 6, who acts the most ideal? The most ideal is the slowest. I'm sorry, the fastest. So that's the lightest gas. So you'll get that. Who's the most real? Just talked about that. List the requirements for an ideal gas. How do I change a real gas into ideal gas? I've covered that. What's the density of CO2 at STP? This is an interesting question. Density is equal to mass over volume. So let's pick 1 mole. At 1 mole, what's at STP? What's the volume? 22.4 liters. So plug that in. What mass am I going to use at 22.4 liters? What gives me 1 mole? The periodic table, formula mass or molecular mass. So try that for size. Notice I can ask for density without giving you any numbers. I'm going to assume 1 mole. And if I'm at STP, I'm going to plug in that because that's for 1 mole. And of course I get the mass per 1 mole from the periodic table. You just plug in and solve. Okay, backside. I know I'm running over 21 minutes, but I'm going to keep going. The rest of these you'll try on your own. What is the rate of effusion? I could say effusion and diffusion between Cl2 and N2. Okay, so I'm going to have the rate of Cl2 over the rate of N2. Now, Graham's law, it's an inverse relationship. I need the molecular mass of Cl2. Well, each Cl is 35 in the periodic table, so this will be 70 grams because the formula is what? The rate of gas A, rate of gas B is equal to the what? Molecular mass, inversely related, of A, molecular mass of B. Okay? So I'm just plugging in from what we just talked about. It's an inverse. It's an inverse of its molecular mass. So it's the square of the inverse of its molecular mass. Any case. So back to reality here. N2, well, molecular mass of N2, atomic mass, I should say, the relative atomic mass is 14. When it bonds to itself, it's 28. Look what I got here. Probably simple math. So let's grab our calculator. Okay, so when we do the math, I get the square root of 0.4. Okay, I just found that number and do the square root key, no problem there. And I get 0.632. What does that mean? Chlorine escapes, compared to N2, 0.632 times. Edit. To 1. What does that mean? Is it going faster or slower? It's going slower. It's 0.63. Now, people don't like this. Okay, so let's do the inverse of 0.63. Okay, 0.63. Let's do the inverse. Let's go find what 1 over 0.63. Meaning, if I did the problem setting it up this way, N2 over Cl2, notice the molecular mass would be 28 over 70. So if I did the problem the opposite way, what value would I get? Well, just do the x to the negative 1 key. So we would come up with a 1 over 1.6. So let's do that. So clear that. Take my 0.632, hit the x to the negative 1 key. Look at that. When I hit my x to the negative 1 key, I get a 1 to 1.58. Okay, both of these say the same thing. If you look at the way that we just did it, chlorine escapes out of an opening faster than N2, 0.63 times. That means it's terrible. Or nitrogen escapes 1.58 times faster. Some people like that. They don't like less than 1, but they say the same thing. So when you do this problem, the math is simple. What does it mean? Chlorine, because it's heavier, okay, escapes or effuses or diffuses 0.63 times that of nitrogen, or nitrogen escapes 1.58 times faster because it's lighter. Okay, and they both mean the same thing. The x to the negative 1 key, if you don't like the smaller than a number 1 to the 1 ratio. This is a ratio. Okay, How fast? Based on kinetic energy. Okay? We look at other questions. Look at N2. Why don't you try number 13 right now, and then I will show you my answer. So pause your video now. Okay, so I am done, plugged it in, used my Graham's law formula, which is what? The inverse of the square root of its molecular mass. Okay, N2 over O2. N2 has a molecular mass of 28, 14 times 2. Oxygen is 32, 16 times 2. Plugged it in, find the square root of my 1.4, which is this number, and I get 1.07. But more importantly, what does that mean? N2, okay, is 1.07 to 1. N2 escapes an opening or diffuses and mixes through a room faster than O2 by 1.07 times. Pretty close, but it does escape and move faster because it's a little bit lighter than oxygen, and that's what the law is based upon. Please try and fill out the rest of the ditto. If you have some trouble, we will go over it Monday, but you better spend some time on this. I have some form questions, not really questions, that I want you to, not really, that basically apply to both of these two that go together. Thank you for your time.